Hello, this presentation is for WASPAA 2023. I'm Shuichi Koyama from the National Institute of Informatics, Japan. The title of this presentation is Perceptual Quality Enhancement of Sound Field Synthesis based on combination of pressure and amplitude matching. Sound field synthesis is aimed at synthesizing the desired pressure field with multiple loudspeakers. Such a technique is applicable to spatial audio reproduction in a large listening area or personal audio in multiple listening regions. And a large number of sound field synthesis methods have been proposed so far, but methods based on the minimization of squared error have practical advantages compared with methods based on analytical representation derived from boundary integral equations. This is because arbitrary array geometry of loudspeakers can be used in these methods. Representative methods of this category are weighted pressure matching and mode matching. The goal of the sound field synthesis is to synthesize the desired sound field U des of R and omega inside the target region omega with L secondary sources or loudspeakers. Here, R is the position vector and omega is the angular frequency. The optimization problem to be solved is formulated like this. So the first term is the weighted sum of the transfer functions of the secondary sources with driving signal DL. So this term represents the sound field synthesized by the secondary sources. So this cost function J is the regional integration over the target region omega of the squared error between synthesized and desired sound fields. So we want to find the driving signal DL that minimizes this cost function J. However, it is difficult to solve this minimization problem owing to the regional integration. A typical strategy to approximately solve the minimization problem in the previous slide is pressure matching. So first, the target region omega is discretized into n control points. Then the optimization problem for pressure matching is formulated as the minimization problem of the squared error between synthesized and desired pressures at the control points. So here, G is the transfer function matrix between the secondary sources and control points, and D is the vector of the driving signals, and U des is the vector of the desired pressure at the control points. And the second term is the regularization term for D. So this problem is a simple least squares problem, so it has a cross-form solution represented like this. So pressure matching is simple for implementation owing to the cross-form solution, but basically requires fine discretization of omega by control points. It is not limited to pressure matching, but sound field synthesis methods basically suffer from spatial aliasing artifacts owing to the discrete placement of the secondary sources. Since the number of secondary sources is usually limited, the synthesis accuracy decreases at high frequencies. This is an example when synthesizing a spherical wave by 12 loudspeakers at 800 Hz. So the left figure is the desired pressure distribution, and the right figure is the pressure distribution synthesized by pressure matching. as you can see, the synthesized pressure distribution is distorted because of the insufficient number of loudspeakers. The spatial aliasing artifacts can lead to the degradation of sound localization of listeners and also the correlation of source signals, which means the timbre of the synthesized sound can also be distorted. To perceptually alleviate the spatial aliasing artifacts, we consider synthesizing amplitude or magnitude distribution at high frequencies, leaving phase distribution arbitrary. This is because interaural level difference, ILD, is the dominant cue for horizontal sound localization above 1500 Hz, compared with interaural time difference, ITD. In addition, amplitude response from the primary source to the target region should be accurately synthesized as much as possible rather than phase response to alleviate correlation effects. So we focus on synthesizing the desired amplitude distribution rather than complex pressure distribution at high frequencies. To achieve this, we consider applying amplitude matching for high frequencies. So amplitude matching, which was previously proposed for multi-zone sound field control, is aimed at synthesizing the desired amplitude at the control points. By leaving the phase arbitrary, the number of parameters to be controlled can be reduced. The optimization problem of amplitude matching is formulated like this. So this sign represents the element-wise absolute value. So this term is the synthesized amplitude, and this term is the desired amplitude at the control points. Then the first term evaluates the squared error between synthesized and desired amplitude as the control points. But unfortunately, this optimization problem does not have a closed form solution owing to the non-convex and non-differentiable cost function. But majorization minimization or MM algorithm or alternating direction method of multipliers, ADMM, can be applied. A proposed method for perceptual quality enhancement is a combination of pressure and amplitude matching. The optimization problem is formulated as a weighted sum of the squared error of pressure and squared error of the amplitude at the control points. And the weighting parameter beta is determined so that beta equals 0 for low frequencies, which corresponds to pressure matching, and beta equals 1 for high frequencies, which corresponds to amplitude matching. For example, beta can be defined as the sigmoid function like this. Here, omega t is the transition frequency from pressure matching to amplitude matching. And this problem can still be solved by MM algorithm or ADMM. First, we show the results of numerical experiments. We simulated a 3D free field, and the target region omega was a cuboid of 1 meter by 1 meter by 0.04 meter. And 32 loudspeakers were placed on the borders of squares of 2 meter by 2 meter at heights of 0.1 meter and minus 0.1 meter. 1152 control points were regularly placed over omega every 0.04 meter. And the desired sound field was a sound field generated by a point source at this position, 2 meter, 0 meter, 0 meter. And we compared the proposed method and pressure matching, which is noted as PM. So first, we evaluated the ILD of the synthesized sound field. The binaural signals in the synthesized sound field were calculated by using the transfer functions from the loudspeakers to a listener obtained by an acoustic simulator called Mesh2HLTF. Then, for the evaluation measure, the normalized error NE of ILD at each head position was calculated like this. So the normalized error of the ILD is averaged over the listener's head direction phi h at each head position RH. And this figures as a distribution of NE on the xy plane at z equals 0. So the ILD error of the proposed method was significantly reduced from that of PM. And this plot is the amplitude response from the virtual point source to the origin, which is the center of the target region. So as you can see, the amplitude response of PM was severely distorted above 1500 Hz, but that of the proposed method was close to a flat response as desired. And second, we showed the results of listening experiments to evaluate the perceptual quality. We developed a loudspeaker array system that has the same configuration as that used in the numerical experiments. And the desired sound field was a sound field of the point source at this position, 2 meter, 0.5 meter, 0 meter. The reverberation time of the room was 0.19 seconds. And we conducted muscular test with 14 male subjects in the 20s and 30s. The listening position was approximately at the center of the target region, but the test participants were able to move their heads on their chair freely. And the test participants were asked to rate the difference between the reference and test signals of 10 seconds. The reference and test signals are summarized like this. So the reference signal is the source signal from the reference loudspeaker here, which is placed at the virtual point source position. And C1 is the low-pass filtered source signal as hidden anchor. And C2 is the synthesized sound by PM. C3 is the synthesized sound by the proposed method. And C4 is the hidden reference. And here are the box plots of the scores of two source signals, vocals and instrumental. So the median score of the proposed method was significantly higher than that of PM for both signals. So therefore, the synthesized sound by the proposed method is perceptually close to the reference sound compared to PM. So here's the conclusion of this talk. Thank you for your attention.